In today's video, we're going to be talking about boundary behavior of light rays, and we're going to just basically visit another topic that wasn't discussed in the previous lesson. So after watching this video, you should be able to understand why some light rays undergo what's called total internal reflection, and be able to figure out this thing called a critical angle that would allow for total internal reflection to actually occur. Okay, so let's get right into it. What is total internal reflection? Well, basically what it is when a light ray is headed towards a boundary between two media, none of it refracts. Okay, so none of it actually exits the media. Instead, all of it just reflects off of the boundary. Okay, so let's say I've got like a fish tank with water in it. Okay, and I stick a laser pen in this fish tank and I shoot the laser, and we know that some of it really should reflect and some of it should refract, exit out into what you will assume is air out here. Okay? Total internal reflection basically means that there's going to be some angle at which this laser can be shot at the water, and it will, none of it actually will leave out into the air. All of it will reflect back into the tank that's like stuck in this water. Okay, and there's some angle at which we can aim that laser at the top of the water that will allow that to happen, and that is called the total internal reflection, or this idea is called total internal reflection, where basically this incident ray of light traveling from the laser does not leave the water. It stays in it. All of it reflects. Okay, and typically there's some specific value for this incident angle, and we'll call it the critical angle that yields an angle of refraction of 90 degrees, basically meaning that none of the light is refracted. Instead, it's all reflected. You know, there's a lot of R words here, but that's what we're looking at for today. Okay, is this idea that basically light cannot escape the media that it's in if you shoot it at the media at a certain angle. Okay, and we're going to call that the critical angle. So let's take a look at an example right here. Out in this picture, there's a laser over here, okay, and it's shot into, this is like a semicircle tank of water. Okay, so this is water in here. Okay. And you'll notice as the laser is in air right here, it heads into the water, no problem. Okay, and here's the direction of the angle of incident. Okay, so it enters into this new media, the water. It strikes the wall over here, and you'll notice you do not see any laser over here. Okay, well, why is that? Well, all of the laser reflected off of the wall and stayed in the water to eventually then come out over here. Okay, but there is none over here, and the reason why is that there was no refraction. We have all reflection. Okay, and that's what we're talking about today. So how can this total internal reflection happen? Okay, and it only can happen when the following conditions are met. Okay, so there's two rules to this occurring. The first rule is that the light is in a more dense medium and it's approaching a less dense medium. Okay, so what does that mean? Well, it means that if I go back to this previous picture, air is a less dense medium than water. Okay? And so this laser will always be able to refract into the water, okay, because it's going from a less dense to a more dense medium. But once the laser's in the water, now it's in this more dense medium, it certainly could undergo total internal reflection because it's going from a more dense medium to a less dense medium, that being air. Okay? So that's rule one, is it must go from a more dense medium to a less dense medium. The second rule is that the angle of incidence is greater than the critical angle. Okay, so the angle at which the light ray is headed towards this the second medium it's got to be greater than this thing called the critical angle. And if you're wondering how to calculate the critical angle, and that's a good question, we're going to be using this formula right here, and it's really kind of a spin-off of Snell's law, if you will. The angle that's the critical angle, theta critical, equals the inverse sine times the index of the refractive medium divided by the index of the incident medium. Okay? And basically, whatever that equals, that is the angle at which, if you shoot a light ray beyond that critical angle, so let's say it's 40 degrees. If you go beyond 40 degrees, you're going to get total internal reflection. Okay? So let's do a practice problem to kind of see what you guys have learned so far. It says for each combination of media, which light ray, A or B, will undergo total internal reflection if the incident angle is gradually increased. Okay, so let's look at practice A first. It says the index of refraction is greatest in medium 1. Okay, so what that means is the n in medium 1 is big. Okay, it's got a bigger n than say in medium 2. The n would be, we'll call it small. All right, and I have no numbers to really put in there, but we'll call this n up here big and this n down here small. Okay, so would this light ray A, as it enters into medium 2, be able to undergo total internal reflection? And the answer is yes, it would. Why? Because it's going from a index of refraction that's big to an index of refraction that's small. That's following rule number 1 in the previous slide. Could it happen here where this light ray B is going from a small index of refraction to a big one? And the answer is no, because it's going from a small to a big n value. Okay, and remember, n is actually looking at how optically dense the medium is. That would be from a previous lesson that I talked about that. Okay, so this light ray B will never undergo total internal reflection because it's going from a small n to a big n, whereas this A certainly could because it's going from a big to a small n. Okay, let's look at practice problem B. It says medium 1 is more optically dense. Okay, so 1, this is more dense here, and 2, it will just call less dense. Okay, now again, keeping rule number 1 in mind, could A, incident ray A, undergo total internal reflection if the angle was correct? And the answer is yes. Why? Because it's going from a more dense medium to a less dense medium. Could B do it? The answer would be no, because it's going from a less dense to a more dense medium. There is no possible way for this light ray B to undergo total internal reflection because it's going from a less dense medium to a more dense medium. That would be breaking rule number 1 in the previous slide. Okay, here is a practice problem for you guys. It says calculate the critical angle for crown glass if it has an n, or index of refraction of 1.5, and it's going from crown glass to air, which has an index of 1. Okay, so let's draw this baby. We have some crown glass here. All right, and we have a light ray headed towards this boundary. Okay, and this is air out here. What will the angle be? What does this angle have to be with the normal? So this theta right there, what does that angle have to be so that actually this light ray will not actually exit out into the air? Well, let's use that formula that we wrote down in the previous slide. Theta critical equals the inverse sine times the index of refraction, NR, so the refractive index of this medium, divided by the incidence index, okay, which is the glass. Okay, so plugging numbers in, we don't know, like I apologize. We know that NR is 1.0 because that's the index of the air. Okay, that's what it's going into, divided by what is the light ray in right now? Well, it's in the crown glass. What is its N? It's 1.5. Okay, and we're going to basically take the inverse sine. Sorry, this is so smushed. Of this to basically get an angle, and that angle equals about 41.1 degrees. 41.1 degrees. So what it's saying is, if I had like a light ray in this crown glass, and this angle right there was more than 41.1 degrees, none of the light would be able to escape into the air. It would all be reflected back into the crown glass. Okay, let's do another problem just to again try to practice this a little bit more. Let me change pen colors here just to keep things exciting. It says calculate the critical angle for a diamond with an N of 2.4 going out to an air boundary of 1. Okay, so let's make a diamond here, and I'm just going to make a square diamond. Okay, so that's a diamond. And it's going into air, and we'll say we have air here. Okay, so let's say this light ray is headed out right here. I'm wondering, and that's the normal line that I'm drawing, I'm wondering what angle this light ray has to travel at so that it is stuck in the diamond, that all of the light reflects. Okay, so I'm going to use the same exact formula. Theta critical equals the inverse sine times the refractive index medium, or the index of refractive for the medium that it's going into or that's refracting into, divided by the index of refraction for the incident medium, Ni. Okay, so what is the Nr? It'd be 1. Okay, it's going into air. All right, so it'd be 1 over, what is this light ray in right now? Well, it's in diamond, and the N is 2.4. 2.4. And we would take the inverse sine of this division problem to then get a critical angle of, if you do the math, you would get about 24 degrees. I believe I rounded that answer, but it's about 24 degrees. Okay, so a pretty low angle in terms of which the light ray can still, or in terms of the light ray being stuck in the diamond. And this may kind of answer the question of how come diamonds are always so sparkly. Well, it's because light gets stuck in diamond really easily, and it's hard for it to get out. So that light ray may bounce around a few times in here before it finally is able to escape, and all that bouncing around makes it seem like it's almost like shimmering, if you will. Okay, so that takes care of today's video. I will see you guys next time.